Hello, I'm Dan Anderson from Intel Corporation. Today I will discuss application development using Hyperledger Sawtooth. As an example, I'll show development with a simple application called SimpleWallet, which just builds wallets and has transactions within and between the various wallets. So we'll start with the basics of Sawtooth, then move on to application development. And I'll do a code walkthrough of SimpleWallet, and then we'll run the application. And then we'll look at some of the data, the transactions and blocks. And finally, I'll have a list of resources for more information. So here's a high-level architecture, just so we understand the application development later. Basically, we have a Sawtooth node in the center there, which consists of several components. You could have one or more transaction processors of various, or of one or more transaction families. You have a REST API on the upper left there, which communicates with the clients. And then you have a consensus engine, which decides which block gets published. And inside the validator, you have various parts, managing blocks and states and communicating with the other components. On the lower left, you have other validator nodes. And each of these other validator nodes are peer nodes, and they look pretty much exactly like the node there with transaction processors and other components. And finally, on the upper left, you have clients which communicate with a node and create transactions, and also could read state using the REST API. SDKs in Sawtooth are available in multiple languages, so you could have a choice of what language you want to use. SDKs are available in Python, Rust, JavaScript, C, C++, Java, Go, and .NET. And they're available for the client and the transaction processor. The client is what creates and sends transactions to a node. The validator node processes the transaction using the transaction processor and then writes it to a state. So the part that you write as application developer is the client on the left and the transaction processor on the right. Think of it as of client and server. So application development. There's concepts of the transaction lifetime, the transaction family, transaction processor, client, and data model. So the lifetime of the transaction is when it's created and consumed by the transaction processor. The transaction family, it's created by the client. A transaction is created by a client. The data model is defined by the application. It's usually encoded using some serialization method, usually Google protobufs, to serialize one or more items of data into one data object and kept in global state in a blockchain. The business logic is coded in the transaction processor, which processes each transaction. The client, as I said, submits transactions and also could read state to find out what the current value is of any object. And that's all done through the REST API, a standard API used in web applications. We have transactions, batches, and blocks. Transactions are just transactions created by a client. You could batch these transactions together for efficiency and also to kind of, if they're kind of coherent related transactions, you could batch them together. And they're written to a block in the blockchain. The data model is up to the application. There's the serialization, how it's serialized, and that's usually defined. Usually, Sawtooth uses protobuf, and that's what we recommend for your application. But there's simpler schemes available. For example, comma separated values, CSVs. So that's just several items separated by a comma. That's very common in spreadsheets. Addressing scheme is also defined by the application. So you have this 6 hex character prefix, which is defined for each transaction family. And after that, how you address each object is in the remaining bytes is usually the hash of the object name. So, and again, that's defined by your application, how you address each object. So transaction families encapsulate the business logic on Sawtooth. There's 3 parts. The client, which you write, the transaction processor, which you also write, and also the data model, which is how the data is encoded in state, and also how the data is encoded in a transaction as it's sent from the client to the transaction processor. Sawtooth allows multiple applications to exist on the same blockchain. You can have 1 or several applications on the same blockchain if you wish. And these could be very simple transaction processes, or it could be something as complex as, say, Seth, which is actually an interpreter that reads and executes EVM or Ethereum virtual machine contracts. The transaction processor, API. There's basically 3 API calls, 3 or 4 API calls there. The first is register. That registers a transaction processor to the validator. So the validator knows that this transaction processor is there. Usually there's multiple transaction processors. And for efficiency, you can even have more than 1 transaction processor for the same transaction family, and that allows parallel processing, or one way allowed. Another way is with threading. There's the apply function. So the validator calls a transaction processor when to apply a transaction, process a transaction. And that transaction is processed using get and set state calls from the transaction processor to the validator. So it gets some objects like reading, for example, some account balances, maybe add and subtract these balances, then it would set these balances using the set state call. So basically that's just reading and writing from global state. The register and apply functions are inherited from the base class. The only thing you really need to, the register and get and set state calls are inherited. As a developer, you don't write those calls. The only one you do write is a apply function. And the apply function processes a transaction. A client. A client submits transactions, and a client also reads or if it needs to read the current values in global state. The primary job is the former. It's to package up and sign and ship off that transaction or a group of transactions or batches. The second part is clients could also retrieve state information to learn the current value of 1 or more objects. And that does not involve the transaction processor. That just involves a query to existing state without modifying it. So, and the way you interact with the validator is with the REST API, which is a very familiar interface for web developers. And we have a rich set of REST API commands for posting and retrieving transactions and state. So here's an example, or here's some of the more frequently used REST API commands. There's a full list in the documentation under Sawtooth REST API, but basically you use two in your client, post and get. So post is what you use to post a batch, or that is a batch is one or more transactions. You always have to have a batch. Even if you have just one transaction, you just have a batch of one, or you could have a batch of several transactions if you wish. Then if you want to read state, you would do the get API call and pass it the state address and then return it back to the client for it to interpret and display. So the client creates a transaction in a batch, and you always wrap a transaction in a batch, even if there's just one. The transaction payload is the main field there for transaction, and that is this free format. It's defined for a transaction family and completely up to you. Then you need a header signature, which and a header. First, you define a header there, which gives various information about the transaction, like the public key used to sign it, any dependencies there may be on other transactions, the transaction family name and version, inputs and outputs, which is important. Those need to be set. That inputs list the inputs of that this transaction is going to read, and outputs list the outputs that this transaction is going to write. These are very important to set. If you don't get to set them, you get an error. And this allows for parallel processing. If the validator knows the list of inputs and outputs of each transaction, it could process transactions in parallel because it knows these very separate transactions will not conflict. If they do conflict, it will process them in serial mode, but usually it could process transactions in parallel where there's no conflicts, and that is an optimization. It's also a safety feature. You make sure your transaction does not overwrite data where it shouldn't. Then another part of the header is just your SHA-512 checksum of the payload, the public key of the signer, and then you have the header signature in the transaction, and you have multiple transactions if you want, or just one, and that's put in a batch, and the batch is what's sent to the REST API. Transaction families, data model. So that's again defined by the application. It's one part of the data model is the serialization or encoding scheme. You could use CSV, comma separated values, CBOR, which is a simple encoding scheme, protobus, which is what we recommend, that allows all sorts of elaborate structures and fields in a transaction, and it also has advantage of being language independent. So you could write your client in one language and your transaction processor in a separate language. The addressing scheme is a prefix followed by a hash of some namespace. So the first 6 hex characters is usually the hash of the family, a SHA-512 hash of the family name, truncated to 6 characters. And then you have on the remaining 32 hex bytes, the SHA-512, a truncated SHA-512 hash of some object name. And these object names need to be unique, and you define these object names in your transaction families, and they're hashed to form the address for the prefix. The hashing, of course, must be deterministic. Every time you hash the object name, it will come up with the same name. And you also must avoid address collision, and that's usually not a problem given the length of the hash there. about 256 bits, which with the birthday paradox and all, usually is not a risk of collisions, but you can allow for collisions if you want to, or just want to be safe. Both the transaction processor and client share the same data model and serialization. The client sends transactions, and the transaction processor must be able to decode those transactions, and then also write to global state. So there's two encodings. One is the actual payload of the transaction. Another encoding is the data is actually written to global state, and that's defined by your application. So I will show a example Sawtooth application, introduce the application, and do a walkthrough of the client and transaction processor and show some of the output. SimpleWallet is a simple bank account application. You define multiple users, each with their public-private key, and they could create their own wallet, and they could deposit and withdraw money from their wallet. And they can also transfer money from their wallet to another wallet. So this is not a digital currency scheme. It's mainly an accounting scheme. So you keep track of transactions and you create transactions between people, and they could add and subtract from their own wallet as you can any accounting software. The transaction processor is available, written in multiple languages: Python, Rust, Java, JavaScript, Go, or C++. You only need to look at one language. They're written in multiple languages just to illustrate that the API in various languages, but they're duplicate implementations. So the Rust implementation or the Python implementation are standalone. They don't. So the transaction processor is not written in 6 different languages. It's written re-implemented in different languages, but each are kind of they're standalone examples. We only have 2 clients, a Python client and a JavaScript client. The JavaScript, usually you write a JavaScript client if you want your application running on the web, and a Python might be used for quick prototyping or to use in more of a back-end environment. So we will only focus on the Python example or that's written here. But the concepts are the same for any language. The SDKs for all the languages are very similar, just that they adapt to the quirks of each languages. So the supported operations for this application is deposit to a client account, withdrawal from a client account, and you can transfer from one account to another, and you can also query a specific account or a specific wallet. The API here is kept simple because we're not illustrating an application, we're illustrating how to use the Sawtooth API SDK to get you up to speed quickly. So we're not going to clutter this example with unnecessary details of any particular application. We just want to show you how to use the SDK for Sawtooth. The client application just creates a deposit or withdrawal or transfer operation. It wraps that transaction up in a batch and sends that batch to the REST API via post query. To find your balance, you don't need to talk to the transaction processor or create a transaction. You just query the REST API for the value kept in global state. So for queries, there's no modifying the global state. You're just querying what the current state object is. The transaction processor executes the deposit, withdrawal, and transfer operations, but as I said, it doesn't need to do balance because that is just a state query from the client. The global state holds key value pairs, address, and some data object. In this case, for SimpleWallet, just the amount for all objects, and each wallet is addressed by the client key, hashed with SHA-512, which I'll show you later. The Git source is kept in a repository at this web address, so you can look at the source yourself and even clone it and modify it as you wish. So let's start with the client, then we'll move on to the transaction processor. So the first thing we do is we create a client. This is creating a client class using optional key file name, and that key file identifies a wallet. So, and we read the key file to get the private and public keys. We open the file, read it. We extract the private key from the key file, as you see here, using decode it from hex and then save the private key. We also extract the public key, and it's kept in the header for the transaction, or saved in the header. And we also have the client address. The way we address these objects is we take the public key and we hash it with SHA-512 and take the first 64 hex characters of that hash. So that's just kind of our arbitrary addressing scheme. Your application could use any other addressing scheme it wants to, just as long as the objects do not conflict or do not collide to the same address. So the address for a SimpleWallet object is the 6 hex character prefix, which is always the same for SimpleWallet transaction family objects. That is, it's the hash, first 6 hex characters of the hash of SimpleWallet. Then the remaining 64 hex characters are the truncated SHA-512 hash of the public key used for that wallet. So I will walk through the deposit code. The withdrawal code and transfer code are very similar, but I would just focus on deposit. So we call a function that I wrote here called wrap and send to do a deposit. We send it the keyword deposit to this function and the value. And then wrap and send, all that does is just wrap deposit and value in the payload and creates a transaction with those 2 items. The encoding is the CSV, comma separated value, so they're joined together. The result is, for example, we're depositing 5 units. We would have deposit, comma 5 as a payload. So it's very simple encoding. And then we also create the input and output addresses of this transaction. Since we're doing a deposit, the input would be the address of the wallet. Since we need to read the old balance, if there is any, then we also need to write to that same address. So for a deposit, the input and output addresses are the same because we would read the current balance, add to the amount deposited, and write that new balance out to that same address in global state. So for this very simple transaction, the inputs and outputs are the same. There's one input and one output. So next we create a transaction header. We put the public key in there, the family name and version, input and output list, which is in this case the same. It's just the address of that wallet that we're depositing to. We have the hash of the payload, which is the payload again is just deposit, comma 5 for depositing 5 units to the wallet. the transaction header is serialized, and then we move on to the transaction header, the transaction itself, which consists of the header that we just created, the payload, which is just deposit, comma, 5 or deposit, comma, 10, depending on how much you're depositing, and the signature of the header to make sure that, well, that just make sure it can't be altered, that you sign that header. That means both the header and the payload itself cannot be altered without modifying the signature value. So we add this transaction list, and the transaction is put in a batch header. This is a very simple batch with just one transaction. And then we create a batch list with just one batch. You can have multiple batches if you want, but in this simple example, we just have one. And we sign both the batch and the transaction. And at the upper corner there, you see send to REST API. So we use the batches command, which is the REST API command, and we give it the data, which is the batch list, which contains one batch and one transaction. So this, once it's the transaction is sent to the REST API, that is then forwarded to the validator part of the node, and the validator then calls the transaction processor using the apply function, sending this transaction to validate that this transaction is legitimate and to do any processing required for the transaction. So the apply function first extracts the header, then the payload from that transaction. It creates a list. It splits the transaction with using the comma character there, because it's a simple comma separated values, and now you have an array of what's in the payload. And the first item in that payload is the operation name, and the second item is the amount. So in our case, for a deposit, it would be the keyword deposit for operation, and amount would be some number. The from key is the public key of the signer, and that's used to read the object and state, and also write to it. So if the operation is equal to deposit, it calls the make deposit code on the next page. The other operations would be withdrawal and transfer from one account to another. So let's look at make deposit, which processes a deposit operation. So we get the key for this wallet and print some debug information. And that would be printed out if you have debugging enabled with the -v option. The current entry is the current value in global state. So it reads global state using the wallet key. This wallet key is a hash of the public key and the prefix for, sorry, the wallet key is the 6-character prefix for this transaction family, and the remaining 64 hex characters are just the 64 characters of the hash of the public key. And your application could use any other addressing mechanism it wants for that transaction family. So we look at this entry, and if it's empty, there has been no deposit made. So we're creating a new deposit for the first time. So we just set the new balance to the amount that we're depositing. Otherwise, there's some entry there already. So what we do is we get the balance, that is convert the value there as an integer. The objects in this, for this transaction families, are very simple. They're just integers, but you could have something more complex. But in this case, they're just strings of integers, and we decode that string and convert it to integer, and we add on the amount that we're depositing, and that's the new balance. Then we encode that new balance, and then we get the address, which is the same address that we read from. And we let's see, we call set state. So set state writes that new value to the global state. So that would be the new balance. So there's a little subroutine we have at the bottom, which is get wallet key. So that's just a simple way of creating the address in global state. And the address in global state is the first 6 characters of the family name of SimpleWallet. That's always the same. It's a SHA-256 hash of SimpleWallet. First 6 hex characters of that, and then we have the hash of the public key, truncated as first 64 hex characters. So the entire address is 6 plus 64, 72 hex characters, or 36 bytes. So here's an example of running SimpleWallet. First, we clone the repository to our Unix system here, or Ubuntu Linux 16 is what's supported right now with Sawtooth 1.1. After we clone it, we change the top level directory of the repository and do a docker compose up -- build, and that builds all the Docker containers used in this application. And that takes a while the first time you run it. After that, it's a lot faster. Then we start a bash shell and go into the client container, and we start our client application. It's called SimpleWallet, and we could do multiple operations. In this case, we first need to generate a key for Alice. That would be the name of a wallet, and we deposit 100 units into Alice's account. And that what that does is it creates a transaction, creates a batch and a batch list, and it posts that batch list using the REST API. And then the response comes back and it tells us whether the batch was posted successfully or not. Later on, we could query that wallet and see how much is there. And as you can see, the result is 100 units because, well, that's what we just added to the new wallet. And that the query just uses the REST API get command to get the state at that address, and then the application decodes that value and prints it out. So here's more detail on the REST API. Here I'll run a deposit of 99 units to Alice's wallet. So you can see a post command using the batches REST API, and that posts the batch list that we created. Then a simple wallet that balance that does a query of the REST API. So here's some other Sawtooth commands I'll show you that's very useful for debugging your application. So here's Sawtooth batch list. What we just did was 2 transactions. We deposited 100 units and 99 units to Alice's account. So you see 3 batches there. One was created in a Genesis node when the Sawtooth blockchain was created. Another 2 batches are the 2 transactions we had. We could show on one batch. So let's show the last batch we created. That's at the very top. So you can see the signer public key and the name of the family, SimpleWallet, list of the inputs and outputs. But the interesting part of this batch is the payload. You see that ZGVWB, which is encoded information. So that's encoded using base 64. So we could find out what's inside there by decoding it. Here's a very simple one-line Python program that decodes that string. And what is in that string decoded? It's just deposit comma 99. So that's your comma separated transaction. It could be it's your keyword followed by one or more amounts. So for deposit, just deposit comma 99. That just means that transaction we deposited or tried to deposit 99 units to this account. We could also show what's in state. So in this case, we have Sawtooth state show and some address. The first 6 characters is 7E2664. That's the prefix used for the SimpleWallet transaction family, and the rest is the hash of Alice's wallet. And we show it, and what we come up with is 199. So it's very simple encoding. We just encode the amount by converting the integer to a string, 199, and that's all that's there. But you can also use more elaborate encoding and in serialization with any method you choose. Then finally, I list the blocks there. There's 3 blocks there. The 0 block at the very bottom is the Genesis block created when you first initialize and create the blockchain, and the other 2 blocks are those 2 transactions we did. So let's do a live demo. To demonstrate this, you could do it yourself. You first do a git clone of the repository. Then you change to that directory. I forgot to put CD. CD to Sawtooth-SimpleWallet. Then you do sudo docker-compose up minus build. That's 2 minuses there. Then you could execute in another window. You would execute a client, so you could do your operations and deposit, withdrawal, or whatever. And later we'll review the logs and we'll look at the batch and state of Sawtooth. So bear with me here. I got to switch windows. Always a fun thing to do. So let me change sharing here. Let's share to, see if we can find it. Let's see, how about my screen? Hard to find sometimes. How if I just share my screen? Bear with me here. Okay, so we have SimpleWallet here, repository. It has several files there. You could see implementations in several languages. We have C++ transaction processor, Go transaction processor, Java, JavaScript, and we also have a Python client and a JavaScript client. Usually, you could write both your client and transaction processor in the same language, but usually you want them to be separate languages. You would want a JavaScript client for web applications and maybe a Python client for non-web applications. If you want simple, fast prototyping, you want to write your transaction processor in Python. If you want something that's efficient for high throughput and transactions per second, you would probably want something that's compiled like Go or Rust or C++. Usual method is to first write your transaction processor in Python as proof of concept, and if it works out, you just could rewrite it in Rust or some other compiled language, and that's very doable because the format of the transaction is language independent, especially if you use protobuf. So protobuf allows reading and writing of buffers, transactions in any language, and doesn't. It's very transparent to write and read from separate languages. So let's do a Docker. Let's start it. So I already built the containers just to save some time. It takes about 5-10 minutes to build and create these containers. Docker PS kind of shows all the containers, or should, if I remember my password. Docker PS minus A. They're not running, so I gotta say Docker PS minus A to show what's there. So we have a client container, just runs the client application. We have the REST API, settings, transaction processor. Sawtooth has one required transaction processor. The settings transaction processor always needs to be running on every node, and that's in addition to your application-specific transaction processor, which in our case is a SimpleWallet processor. And finally, we have the validator component. And we would this is for Sawtooth 1.0. For Sawtooth 1.1, we'd also have a consensus engine. In this case, it'd just be dev mode consensus, but it could also be another like Poet or Raft or whatever. So let's start it here. A little shell script here. So we just run Docker compose. And just let it fly if I did, except I made some typos here. Let's just cheat and copy and paste. So we specify a .yaml file, and this one is specifically to run a Python transaction processor and Python client. And this should be pretty fast because I have not modified any of the code and already built the client and transaction processor. Although it's taking its own sweet time here. So it built first here. Let's see what built a client container. It's built the Python transaction processor. Now it's starting the settings. So REST API, and now we have the debug output displayed here. And at the very left, you could see where the debug is coming from, what component. So, and then we need to switch windows to run the client. same directory. So let's just run let's see, sudo docker exec. You specify the name of the container and bash. So it just starts a bash shell on this container. So let's start by, let's see here. Bear with me here. Okay. Tooth, keygen, Alice. Generate a key pair for Alice. And then we do a deposit with our client. And as you can see, what it did is create a transaction and put that in a batch list, and posted that batch list to the REST API, and the response came back. Then we could query the blockchain with the same client. And we have 100 units. So let's say we want to make a little change here. So let's stop our Docker containers with a simple Control-C, wait for it to all settle down, and write back and save the state. Okay, so let's pwd, let's go back to this window. Let's go to py client, okay, and then let's see, vi. Go to simple wallet client.py. Let's look at inputs list here. So we get, in this case, we just set inputs to input address list and output address list, which is just the address of that wallet. We could set outputs to everything. So, for example, we have a transaction we're not sure where it's written to. We could just say, or read from. Let's set the inputs to possibly everything, which is not recommended. But if you have a transaction and you don't know what it's reading, you just set it to the empty list, which is different from not setting it at all. Inputs and outputs have to be set to something. So use that annoying notice. So inputs with one item on the list there. Where's my prompt here? Okay. Inputs is set to an empty list of one item, or a list of one item that's empty. Outputs, let's set it to the prefix. Let's see, 0. There's a prefix. Okay. So outputs, we'll set it, has to be a set, so we put it in closing parentheses. And this output list has one thing, which is the prefix of the transaction family. If you really don't know your inputs and outputs, you could just set both of them to your family name, because a transaction processor in most cases would not need to write outside the address, its address space. So yeah, okay, that should be better there. Yeah, forgot the comma there. Have to have the syntax right, to have the brackets right. Okay, I think it's right this time. Let's start it again and wait. Rebuilding the client again after that one line change. Okay, almost. There it goes. Okay. Let's run client shell again and try SimpleWallet. Deposit 400 this time. Gotta type it correctly here. Okay, looks like it worked. Let's verify that. SimpleWallet balance. Okay, so she has 500 units in her wallet now. So let's get out of the shell there. And let's let's look around here. So we have Docker. You can see the containers that we're running. Let's show the blocks that we have. So we have, how many blocks? We have 1, 2, 3 blocks. The Genesis block, block 0, and the 2 transactions we wrote. There's our transactions there. Let's look at one transaction. Copy that big long ID there. So you can see the key used to sign and the hash for the payload and the payload there. Let's see what's in that payload. Let's copy that. Edit, copy. Sorry, we could just write a little small program to decode that. So I have not memorized. Okay, Python. Sorry. Let's paste that payload right in there. Except I copied the wrong thing here. Okay, let's repain. Okay, let's try this again. Payload. Copy, paste, and copy the payload. Edit, copy, paste. My syntax right here. So I got that right. Let's run that. So that was a deposit of 400 units. I don't know where that 10 came from, but it should just be deposit 400. I think that's a bug. I think it just sends 2 items there when it shouldn't. So let's get back to the presentation. Where is it? There it is. Okay, that's. So what we showed was starting a application, run it with Docker, and we could stop Docker, make some modifications, and restart the Docker containers, and it will update the container with whatever has been modified. Then we looked at the the, the blocks and the transactions using Sawtooth commands. So here's some pointers here for further information. We have the Sawtooth website, sawtooth.hyperledger.org, that points to the documentation and to the FAQ and also to our chat, which is Rocket Chat. The chat is a very good way. If you have questions or problems, you ask your question at the Sawtooth channel at chat.hyperledger.org. We have API reference and SDK reference, which is very important for writing your application. We also have details for batches and transactions, detailed information about batches and transactions. There's also a couple simple application examples. Sawtooth SimpleWallet, which is the application shown here. If you want something a little more complicated, you could go to the Education Sawtooth Simple Supply repository, and that's a supply chain application. And it comes with a set of PDF files that you could read and follow along, and it shows you how to write a simple supply chain application. That's a good next step after you understand and have run the SimpleWallet application. So that concludes this demonstration. And well, oh yeah, there's also, I have other videos. You could look at the same channel for security and for overview of Sawtooth. Look at the channel there for all the other Sawtooth videos. And thank you.